We're now going to introduce Coulomb's law. We have some sample problems here today to go over how to do a Coulomb's law problem. So first is the equation. The force that two charges exert on each other is equal to Coulomb's constant, K, times the magnitude of charge 1 times the magnitude of charge 2, all over the distance between them, squared. So let's read this sample problem. Object A has a positive charge of 6 microcoulomb. Object B has a charge of negative 3 microcoulomb. A distance of 3 centimeters separates the two charges. Calculate the force on object A. So, we will write the givens. Q1 has a charge of 6 times 10 to the negative 6 coulombs. Charge 2 has a charge of negative 3 times 10 to the negative 6 coulombs. The distance between them is 0.03 meters. Now, I tend to ignore the sign because all the sign is going to affect is whether or not they attract or repel. Now, in this scenario, we're not given a picture, but we know we have a positive and a negative charge. So we know they're going to be attracted to one another. Let's just practice finding the magnitude. The force is equal to Coulomb's constant, which I'm going to abbreviate as 9 times 10 to the 9th, times charge 1, 6 times 10 to the negative 6, times charge 2, 3 times 10 to the negative 6, all over 3 centimeters squared. So go ahead and type that into your calculator. Just as a side note, in your calculator, above the number 7, you'll see a button that has 2 capital E's on it. That stands for enter exponent. So for example, Coulomb's constant, 9 times 10 to the 9, you're going to enter as 9. You'll hit second comma, a capital E will appear, and we're entering just the exponent. So 9 times 10 to the 9, the exponent is 9. And so when you go ahead and plug that in, you should get 180 newtons in your calculator. And that is going to be an attractive force because we had opposite charges, one positive, one negative, and we'll leave that at there for now. Find the force between two charges if they both are 6 microcoulombs and they're separated by half a meter. So again, we're going to be using Coulomb's law here. The force is equal to Coulomb's constant times charge 1 times charge 2 over the distance between them squared. So that's going to be 9 times 10 to the 9 times 6 times 10 to the negative 6 times 6 times 10 to the negative 6 all over 0.5, excuse me, and that's squared. So we'll go ahead and plug that into our, and when we do, we get 1.296 newtons, which I've rounded here to 1.3 newtons. When we do number 4, why don't you try doing number 4 on your own? Pause the video now, try it, and then when you're done, you can play it and Go ahead and plug that into my calculator. And we get 16,000 newtons. If you're asked to find one of the charges, I recommend writing the Coulomb's law. And identifying what it is you have to find. So in this case, we have a charge, so it's a force. We know it's 5 centimeters away. The second charge is what we're looking for. So it actually solved Coulomb's law, multiply both sides by r squared, and then solve that for Q2. So we get Q2 is equal to F, the force, times the distance squared, all over KQ1. So that's going to be 65 newtons times the distance of 0.05 meters, all over the 9 times 10 to the 9. And charge 1 is, we're just going to say 6 times 10 to the negative 6, and we'll deal with the sign later. So I'm going to go ahead and plug that into my calculator. I just had to remember to square the 0.05 meters. And when we plug it in, we get 3 times 10 to the negative 6 coulombs as our second charge. Okay. Object A has a charge of 1.8 microcoulombs, so I'm going to write that. And object B has a charge of, B is a charge of 1 times 10 to the negative 6 coulombs, and this is negative. So before we do any math, we know that they're going to be attracted towards one another. So that means that A is going to be pulled downward. It means that B is going to be pulled upward. Because they are opposite signs, you have a positive and a negative, they're going to attract. Now the force that they exert on each other is going to be the same in amount, just the opposite in direction. So we're going to plug this into Coulomb's law. So I'm going to write Coulomb's law here, just to be a matter of plugging it in. So the Coulomb's constant, still 9 times 10 to the 9. Charge 1 is going to be 1.8. Charge B is 1 times 10 to the negative 6, all over 0.014. We have to remember to square that, just the bottom. So we're going to go ahead and plug that into our calculator. And when we do, we get 82.65 newtons, which I have rounded here to be 83. So the force on A is going to be the approximately 83 newtons down, and the force on B is going to be 83 newtons up. And we have one more practice problem that we can do. Coulomb's law. So object A has a positive charge of 6 microcoulomb. Object B has a charge of 3 microcoulomb. So we have a positive and a positive, so right away you know going to repel. They're going to push away from each other, and they're separated by a distance of 0.03 meters, 3 centimeters. Calculate the force. So why don't you pause the video, go ahead and do that, and then when you're ready, you can start watching. And you can see you're going to get 180 newtons. And there you have it. That's the introduction to Coulomb's law with just 2 charges. Now we can take a look at some one-dimensional Coulomb's law problems. One-dimensional, so it'll just be left and right, up and down. We won't have to worry about combining both x-axis and y-axis in these problems, but we will be able to introduce the concept of multiple charges. In other words, not just 2 charges, there might be 3, there might be 4, etc. So let's go ahead and begin by reading the problem and labeling the important information. So in this problem, charge 1 has a charge of 15 microcoulomb. The prefix mu is going to mean times 10 to the negative 6. So in other words, 1 microcoulomb is 1 times 10 to the negative 6 coulomb. That's very proper size, appropriate size, common size, the microcoulomb for point charges. So you definitely want to make sure that you know that a microcoulomb means times 10 to the negative 6. You should recognize that prefix, or that abbreviation for the prefix, is the Greek letter mu, which of course you remember from coefficient of friction. Charge 2 is 8 microcoulomb. And Q3 has a charge of 10 microcoulomb. D1 is 0.2 meters. D2 is 0.3 meters. So not drawn to scale, but still helpful to have a picture. So in all these problems, you're typically going to be finding the net charge or the net force on a single charge. So in this case, you can see in part C, our goal is to find the net force on charge 2. So part A is figuring out what charge 1 does to charge 2. Part B is figuring out what charge 3 does to charge 2. But in the end, all we really want to know is the net force on charge 2. So in order to do that, we actually have to complete 2 Coulomb's law problems. So we have to do part A. So we have the force is equal to K Q1 Q2 over R squared, where we're just going to look at charge 1 and charge 2. So we have 9 times 10 to the 9. Now what I would recommend here is putting in the first spot charge 2. So 8 times 10 to the negative 6. The order is not going to matter. I just do it for, you'll see in a second why I do it. Charge 1 is 15 microcoulombs. That's 15 times 10 to the negative 6 all over 0.2 squared. So you go ahead and type that into your And when you do, you get 27 newtons. So now we're going to look at the direction of the force. So in this case, we had two positive charges. So I said that I ignore it in the equation because I'm just looking for magnitude. But when we're dealing with net force, or any force really, you're going to need a direction. So you can see that they're both positive, which means they're going to repel. So they should be pushing apart from one another. So Q2 is going to push Q1 this way, and Q1 is going to push Q2 this way. So in this problem, we're finding the net force on Q2. Well, Q1 is pushing it, Q2, and it's pushing it to the right. So this 27 Newton force is to the right. So that's the effect of charge 1 on charge 2. So that's the first half of the problem. The second half is going to be figuring out what is the effect from charge Q3. So we have another Coulomb's law problem. Now the reason I set it up with Q2 as the first charge in the last one is this. So you'll notice 9 times 10 to the 9, oh, that's the same. The next thing is the charge of Q2, which was 8 times 10 to the negative 6. And the next thing, in this case, we're looking at charge 3, which is actually 10 times 10 to the negative 6, all over. Now, how far apart are charge 2 and charge 3? Well, they are 0.3. And you have to remember to square that. So we'll go ahead and plug it in, but wait, you don't have to retype everything. All you have to do is press second enter on your calculator. And what's the only difference between part A and part B? Well, there's two actually. The first is the magnitude of the second charge. So it's not going to be 15 times 10 to the negative 6. It's going to be charge 3's charge, which is 10 times 10 to the negative 6. You'll also have to adjust the distance, which is no longer 0.2, it's 0.3. So if you make those two changes in your calculator, you get 8 newtons. So that's why I do it. I think it saves you time, especially if you had 6, 7 charges. You could really get pretty efficient using that function on the calculator. So now let's consider Q2 and Q3. Are they going to attract or repel? Well, Q2 is positive, Q3 is negative. They are going to attract. So I'll draw those forces up there. So now let's think about this. If you're Q2, you have two forces acting on you. You have, from charge 1, a rightward force of 27. And from charge 2, you have a rightward force of 8. Well, if you have something pushing you right with 27 newtons, something pushing you right with 8 newtons, that means that your net force is going to be 27 plus 8, or 35 newtons to the right. And there you have it. That is how we're going to do Coulomb's law with multiple, or more than 2, I should say, point charges. So go ahead and read problem 2. Go ahead and identify the givens from the question, and go ahead and label them on the diagram. Go ahead and pause the video to do that, and then you can check it with mine in just a minute. Okay, I hope you had a chance to go through and label the givens on the diagram. I think the pictures really help you to understand what's happening. So, one thing that you should notice is that we are trying to determine the net force on Q1 this time. So everything's going to be in terms of Q1. So that means we need to find, Q1 and Q2 over R squared. And then we're going to have to find the force of Q1 and Q3 over the distance between them squared. So this time I actually changed the generic Coulomb's law equation to help with the problem. So that's a technique that maybe some of you will find useful. So right away, I want to start, before we do any math, understanding the directions. So Q1 and Q2, they are both positive, so they are going to repel. So when they push each other away, the force on Q1 will be left, the force on Q2 will be right. Make them in green to be color coded. Okay. And then we want to know the effect of Q3 on Q1. Well, they are opposite charges, so they're going to attract. So they're actually going to be pulled towards one another. So that means that the effect of Q2 on Q1 is repulsive, meaning left. And the effect of Q3 on Q1 is going to be attractive. When they attract, Q1 is going to go right. So without doing any math, I figured out the direction. So the signs do not tell you the direction in the typical sense. Positive does not mean right, negative does not mean left. It's easiest to look at the picture, determine if they are attract or repel, and you can figure out if they're being pulled towards one another, pushed away from one another, and based on what the picture looks like, you can figure out if that's left, right, up or down, etc. So let's go ahead and try this problem. So Q2, 9 times 10 to the 9. Q1 is 15 times 10 to the negative 6. Remember, micros times 10 to the negative 6. And 2 is 8. So the distance between Q1 and Q2, I can get right off the picture, that's 0.2. I need to square it. Go ahead and type that into your calculator, and that's going to be 27 newtons. Now they're both positive, they repel, and as we already talked about, this is going to be left. Now for the next one, Q1 and Q3, we have 9 times 10 to the 9. Charge 1 is 15 times 10 to the negative 6 coulombs. Charge 3 is 10 times 10 to the negative 6. Now the distance between them, you can see, is actually 0.5. You have to add those two distances together. So 50 centimeters, half a meter. And we can go ahead and plug that into our calculator. And again, you can use the second enter function of a TI 8384, and the only thing you would have to change are the 8 to a 10 and the 0.2 to a 0.5. And we get 5.4 newtons when we do that, and that is to the right. So if you're charge 1, and you have a force pushing you, 27 newtons left, and you have a force pushing you 5.4 newtons right, you are going to have to figure out the sum of your forces. Your net force is 27. It's 5.4. So the net force is equal to 21.6 newtons, and the leftward force is bigger, so it's going to be to the left. There you have it. There's your introduction to Coulomb's law in one dimension. Hopefully you found this useful. Make sure you feel comfortable using exponents in your calculator, in particular the enter exponent button, which is going to be very helpful to you. Well, I hope you enjoyed this episode of Coulomb's Law. Have a nice day.